Hey, looking at rotational energy and momentum today, finishing up the rotational physics, carrying everything over from the linear physics to the rotational world. First one I want to talk about here is kinetic energy. In the old world, in the linear world, we had kinetic energy 1/2 mv squared. You will remember that v was equal to r omega, so we've replaced that here. And when that gets squared, then we're taking that mr squared and put it in together. That makes I, and there's omega, so we end up with a rotational kinetic energy 1/2 I omega squared. If you wanted to calculate the kinetic energy of a rotating object, that could be thought of as the energy it would take to get it going, or the energy that it has as it's moving, or the energy that it would take to get it to stop. How much work you'd have to do to stop that thing. Wouldn't matter. You could calculate it up like this. For example, let's say we have a sphere that's rotating about this central axis right here, and we'll say that's a solid sphere. And since we need the moment of inertia here, we'd have to look that up on a table, and the moment of inertia would be 2/5 mr squared. All right, and if we knew the mass was 10 kilograms and we knew that the radius was 1 meter, why then we could come in here and say that the moment of inertia would be equal to 1/2 times 10 kilograms times 1 meter per 1 meter squared, and that would work out to 5 kilogram meters squared. We could put that into the moment of inertia right there. If it were spinning at 2 radians per second or 15 radians per second, faster it's spinning, the more kinetic energy it's got. So just making up a number here, if the angular velocity is 4 radians per second, then I'd want to put that in for omega, and we'd have 1/2 times the 5 kilogram meter squared moment of inertia times the 4 radian per second. Don't forget to square it. And here we'd have 16, 8 times 5, 40, and that would be kilogram meter times a meter. I got a second squared here. Remember, the radians just kind of evaporate. If I bundle up this much right there, kilogram meter per second squared, that would be a Newton. So 40 Newton meters, which turns out to be our old friend joules right there. 40 joules of rotational kinetic energy. That thing is moving, it has mass, it has kinetic energy. If you're considering a conservation of energy problem, that still works, just like it did in the linear world. So here is a 2 kilogram cylinder that's rolling at 2 meters per second, and we find a ramp. Here's the object, and it's rolling this way. We said the mass was 2 kilograms, and the velocity is 2 meters per second, and that thing's going to roll up a ramp here. They'd like to know how high off the ground we get right there. Let's call that H, shall we? Okay. So this looks like an old conservation of energy problem. No big deal. We've got point 1, we've got point 2. We know that the energy at point 1's got to be equal to the energy at point 2, and we say fine. At the bottom I've got kinetic energy, and at the top at point 2 I have potential energy. And so we set that together like that. The difference here would be that at the bottom, that cylinder is doing two things. It's moving forward and it's rotating. I'll draw an arrow for each one of those. The cylinder moves to the right. That would mean it would have regular kinetic energy. Sometimes people call that translational kinetic energy, meaning it moves through space. Plus, it's rotating, it's turning. And then, of course, potential energy at the top. So that's the difference here. If the object is rotating, you've got two kinds of kinetic energy, and you've got to put both of those in. The translational kinetic energy, the old kind, 1/2 mv squared. The new kind is 1/2 I omega squared. And then, of course, potential energy would be mgh, like that. All right. You can see that I is in there. We're going to have to figure out the moment of inertia of this thing. So I look it up on the table. The I is 1/2 mr squared, and we can make that substitution into right there. They didn't give me omega, so I'm going to have to do something for that as well. What I need to do here is to remember that equation that links angular velocity and linear velocity. Right here, v equals r omega, so if I want omega, that would be v over r, and I could pick that up and put it in for omega. Watch what happens when I do that. Here's 1/2 mv squared plus 1/2 I, but I was 1/2 mr squared, times omega, which is v over r, and don't forget to square that, so that'd be v squared over r squared equals mgh. Now all sorts of nice things happen. We didn't know r, turns out we don't need it because it cancels. They gave us the mass, turns out we don't even need it because there's mass in every term, and that cancels out. And we can simplify this down. I've got 1/2 v squared plus 1/4 v squared. That would be 3/4 v squared equals gh. So if I divide by g, well, then I'd have the height, wouldn't I? So 3v squared over 4g would be equal to the height, and you can put the numbers in here. That's not the interesting part, is it? The velocity was 2 meters per second. Squared down here, 4 times, what's going on with my pen? 9.8 meters per second squared. And we'll push some buttons here and get a number, but it's just a number. I got about 0.306. Hope you did too. And of course that would be meters. You can see there's a meter squared and a second squared, and the second squared's canceling one of the meters. So we're about 1 foot off the ground here, I guess, and that would be the problem that we could do there. But don't forget, if that object's rolling, you've got 2 kinds of kinetic energy, and you need to put both of those in. Next up, we've got the work energy theorem. We saw that back in the energy and work stuff. There's the form that we know and love right there. The change in kinetic energy means that there's a change in kinetic energy, and that's equal to the amount of work that it takes to change that kinetic energy. So factoring out the 1/2 and the m, I'd have this much here. Remember that v is equal to r omega, so we've made that substitution. V naught then would be r omega squared, and down here's a nice little version of that. You can see that that would just carry over everything that we've done all semester. All the linear physics comes over to the rotational world. Works out really nicely. That's another example. Here's one. Previously we had P equals mv. The momentum was equal to mass times velocity. Well, there's an angular momentum as well. We used the letter L there because, see, there's an L right there in angular. I don't know why it's L. But instead of mass, we write I. Instead of V, we write omega. And you can do that with crossing all the R's out if you want to, but we'll just do a simple substitution there. We could calculate the angular momentum of this skater. Let's say she's got an axis of rotation right through the center there, and as she spins around, we'd have to know the moment of inertia and her angular velocity, but we could find her angular momentum. It would be a number, and that would be a vector quantity. And here again, this is a right-hand rule thing. That vector, you'd put your fingers in the direction of rotation, and your thumb would point the fingers of your right hand only here. Fingers of your right hand in the direction of the rotation, your thumb would point the direction of the angular momentum. So that's a vector that points upward there, like that. We can conserve angular momentum just like we conserved regular momentum. And you see here that P equals P prime. That's what we wrote back in the momentum chapter. Right there, it turned into this if we had 2 objects. Here, if we had 2 objects that were rotating, L equals L prime would turn into that with those same substitutions. Instead of mass, moment of inertia instead of velocity, angular velocity. More common, it's one object that's rotating. So just scratch this out and that out, and you'd be left with I omega. This should read I prime omega prime. Little omission there. But if you'll forgive me for that, then the skater is a pretty good example of this. Let's say that this is the skater here, and she's got her arms out and she's spinning away. That's a crummy picture. But let's say that initially, before something changes, maybe her moment of inertia is 14 kilogram meters squared. Just made that number up. Here's another one. The omega might be 4 radians per second. So I could multiply that moment of inertia times her angular velocity, and I would get how much angular momentum she has. Well, something changes. Maybe she pulls her arms in, and if you've watched any Olympics or anything, then you know that when skaters pull their arms in, they spin faster, right? So if the moment of inertia goes down as she pulls her arms in, she's bringing that mass closer, and that makes it easier to spin. Let's say the moment of inertia goes down to 8 kilogram meters squared. All right, and we'd like to know what the angular velocity is. Here's a real nice formula. Really easy math, nothing to it. The new angular velocity would be I omega over I prime, and you can see that that would be 14 kilogram meters squared times 4 radians per second, and then we want to divide by 8 kilogram meters squared. The units of moment of inertia cancel out here, and I'd be divided by 2, so this would be 7 radians per second for the new angular velocity. We were spinning at 4, and it went down. Did I get all the numbers right? Guess so. 14. Yeah, okay. Yeah, we're good. And she pulls her arms in, she spins faster. If she puts her arms back out, she's going to slow down. And it's just the way it has to be in order to conserve angular momentum, just like conservation of regular momentum. This is a nice little list here of everything that we've swapped out thus far. We've got all the linear physics here, and we've got all of the angular physics over here, and you can see that they just match up. Here's the 3 formulas of kinematics. This would be the 3 formulas of angular kinematics. Here's Newton's law. Here's Newton's law for rotating object. That's a tau right there. Here's work. You could have work in a rotational sense. Instead of force, you'd write tau for the torque. And instead of distance, it's angular displacement. Kinetic energy, we talked about that one. Momentum, angular momentum, everything just comes over. You can make some simple substitutions here. X becomes theta, V becomes omega, A becomes alpha, F becomes torque. What else do we need? Mass becomes moment of inertia. The momentum becomes angular momentum. And everything we've done all semester, we've got a new physics now that works just like the old one. All right, hope that helps, and I'll catch you next time.